Hello, my name is Daniel Davila. My ID number, my matrícula, it's a01708923. And this is my argumentative exam. I will demonstrate the part A and the part B of the situation number 1. Okay, we begin with the Field-Savart law, which states that the magnetic field generated by a current element is this. Okay. In this setup, the wire is aligned along the z-axis, and the observation point is located at a perpendicular distance. Now we compute in here. We have our diagram, our graph, and then we compute the cross product between dl times r. That gave us the answer that was rho dz a rho angular of rho. I think here it's clear. Okay, then we substituted into the Field-Savart law. We factor out our constants in order to finally get the expression that is this one. That we have the cosine and the sines. And in the part B, I didn't finish it, but I got until segment number 3. We got some conclusions from it. In order to get the segment, we use the vector geometry and the Field-Savart that goes from 0, 0, 0 to 0, A, 0. And here we have the segment. We used also we find out 3 points in order to put it on the general formula for the triangle that was formed in our segment graph. In here I have the 3 segments, segment 1, number 2 and 3. I repeat the same procedure for each segment. That was basically getting the 3 points, then getting the cross factor between the different vectors that were in our graphs, and that was the segment number 1, part A and B. Let me show you very fast the segment number 2. You can see we have here our coordinates, and then we have here the points which we obtained to later on make our cross product to find out the direction of the magnetic field. I know in order to finish this part, we should have added up all the segments, but I wasn't able to do it. But indeed, I did the part that was shown here. I'm gonna pause the video and continue with now part 2. Okay, let's start with situation number 2. Here's the procedure. I will be explaining it part by part. And in this case, the loop is a circle of radius g, and the current flows clockwise when viewed from the positive y-axis. This means the current flows from the positive axis toward the positive x-axis. Parametrizing the loop using this angular variable, that is phi, angular phi. So the position vector of the current element is rotating around your vision in the xc plane. The differential element of current is the dl, as it is explained here. The vector is always tangential to the circular loop and changes direction as speed changes. In here, I observed that it was a polar form inside a Cartesian, a radar vector, a circular. So with that in mind, I was able to change my R into this circumferential coordinates that using rho, changing zeros and x's to this, being able to get out the cross product using the determinant. The result giving us a vector with components in x, y, and z. But the key idea in here is that for every current element at an angle phi, there's another element directly across the loop at phi plus p. And when you add their contributions together, they cancel out. As you can see here, it goes in different sides, canceling out as the angle set goes vertically and the angle rho goes outwards. Now after analyzing all these parameters with the graphs, then we continue with the solving of the integral, in which we have our integral here. We use the data obtained here, which was the changing from Cartesian to circular coordinates, circumferential coordinates with rho, and the cross product, interchanging it to then solve the integral, simplify it, giving us a vector that changes direction as rho changes around the loop. We can tell also the magnetic field at the point 0, y0 is in the positive z direction, while at minus y0 it points in negative. So the magnitude of the field of both points is the same, as the symmetry cancels, telling us the magnetic field around current loops are symmetric but forming a closed loop. The conclusion is the use of Biot-Savart to compute the magnetic field to a circular loop in the XZ plane, the parametrization of the loop using an angular variable, and also the field of at both points that has same magnitude but different direction, canceling them out as the symmetry states. Now I will solve situation number 3, which involves calculating the magnetic field produced by an infinite current sheet of paper using Ampere's law. It relies on the xy plane, as you can see here. And it carries a uniform surface current density K flowing in the negative z direction. We started out with the Ampere's law. To apply it, we define a rectangular Amperian loop that is symmetric with respect to the sheet. We have chosen to the loop in the xy plane with the vertical sides x0 and x0. This carries a surface with current density K that is I between length, that it's current between length. Okay. Then we use symmetry and determine the field direction. We use the right-hand rule. In the direction of current, in the negative z direction, and curl them toward the observation point. The knob points in the y direction, So the magnetic field is at the xy direction. This could be the y direction, it's this, y direction is like this. We make the line in, we determine the symmetry of this and this. That led us to a conclusion that I will talk about it later on. We compute out each segment applying Ampere's law, and the conclusion is the magnetic field is uniform and constant on either side of the sheet. It is parallel to the sheet and perpendicular to the current direction, and it has a discontinuity at the sheet. Here we have also that there is a difference between the symmetry of the second problem that was a closed loop, and in this one there was no closed loop. So I used the Ampere's law to compute the magnetic field. I chose a rectangular loop aligned with the geometry of the problem, and applying the symmetry, evaluating the integral, I was able to demonstrate the magnetic field of the current of the sheet. Now let's continue, but with the situation number 4. Let me show it to you. It involves the motion of a charged particle in a uniform magnetic field. First of all, we apply the Lorentz force. We have some variables, that is the charge, that is Q, and mass, that is M, and also we have the B, that is the magnetic field. It's uniform and points in the negative y direction, as you can see in here. And we used Newton's second law in order to find out the value for the charge and the velocity. We computed the cross product first of all we derived in here this formula to find out the velocity between x, y, and z. After deriving and multiplying with the charge, we did the cross product to find out the charge with the magnetic field. For the force to become this, giving us this system of equations. The last equation shows us an existent acceleration in the y direction that will be shown later on with the graph. Let me explain now the second point, the A, B, and C. The motion of the particle follows a straight path along the negative direction of the y-axis, since there is no force acting on the particle, maintaining a constant velocity. Back again, not only we did it with the mathematical proving, but we indeed combine it with the theory that tells us that when it is constant velocity, we have no acceleration. The entire motion is confined to the y-axis, as there is no movement in the x or z directions, meaning that the particle does not sweep out a plane. In this case, particles have no experience with any magnetic force, as initial velocity is in the magnetic field direction. The motion of the particle as it travels linear along the negative y-axis with a constant velocity, so it is not periodic. I graphic using MATLAB, but in this case it was like a really easy one. It's just a straight line. We have also the velocity that could be sine and cosine, but in this case I just plotted out the acceleration, that it's linear, not periodic. This was the situation number 4. Now I will present to you situation 5. I analyzed the magnetic force acting on a rectangular current carrying loop placed next to a long straight wire. Carrying a steady current I upward. The loop lies in the YZ plane and carries a current I2 that circulates counterclockwise. This will be important in order to make the calculus, the data. So we know we have 4 forces. We added them up by using the Biot-Savart law. We derived each of the forces. And here I can explain we just basically used this circle in order to compute each force. For at the end, add it up, each one. We got to the conclusion that the forces number 3 and also the force number 2. No, let me explain well. Yeah, no, the forces F2 and F4 cancels out each other, as it gave us a negative sign with the circle of the angular of E, rho, and Z. I can also explain that the torque F1 and F3 experience magnetic forces in opposite directions in AZ, but F3 experiences stronger forces as closer to the wire. Torque acts about the x-axis, which is perpendicular to the plane of the loop, and tends to rotate the loop away from the wire, causing a rotational tendency. We can tell this is different from the situation number 3 because first of all, in this case we have one of the forces that will be in more close contact. Okay, in the situation number 7, I can show you like manually the MATLAB code, but I can talk to you about it. I analyzed the magnetic force on each segment of a current carrying wire loop placed inside a uniform magnetic field, forming a square loop with segments labeled as AV, VC, and CD. In this case, with the MATLAB code, I am reading the MATLAB code. Like, if you want to see it, you can see. I can tell the magnetic force on loops. This script computes the magnetic force on each segment of a current carrying loop with different segments. We have the segments, the magnetic field, and displays the force of the loop. I took into account the Biot-Savart simulator that we did in order to compute this MATLAB code, as I thought it was pretty similar, while the structure mostly, and it was easy because of the segments that were chosen, that is accommodation between 1 and 0, and that's all for my exam. This was the situation number 7, and thank you for all and for listening.